This section is 10.1 factors. Okay, so factor is basically when two or more numbers are multiplied, each number is called a factor. So like here, our factors of 12 would be things that we could multiply together to be 12. So like 1 times 12 is 12, 2 times 6, and 3 times 4. So all, how many numbers are there? 6. So all 6 of those numbers would be factors of 12 because they could all be multiplied by something, a whole number, to get 12. Next thing we have here is prime numbers. So prime numbers are whole numbers with exactly 2 factors, itself and 1. So like an example of a prime number would be like 3, because the only thing we can take and multiply to get 3 would be 1 and 3. And we're just talking whole numbers here, so I know you could take like 2 times 1.5 and get 3, but we're only talking about whole numbers. Composite numbers are the opposite of that. So composite numbers are whole numbers that have more than 2 factors. So like 4. So we know we could take 1 times 4 and get 4, but we could also take 2 times 2 and get 4. So 4 would be a composite number. Listed out here are the prime and composite numbers less than 20. So our prime numbers less than 20 are 2, 3, 5, 7, 11, 13, 17, and 19. And then our composite numbers less than 20 are 4, 6, 8, 9, 10, 12, 14, 15, 16, and 18. Now you might be wondering, okay, well, 1 is not on there, right? So 1 and 0 aren't really considered either prime or composite because they don't really fit either of the rules. So 1 and 0 don't really mix into this stuff, okay? It's everything that's above 1 and a whole number. Another thing worth mentioning here is in our prime number list, the only prime number, the only even prime number is 2, okay? Reason being, every other even number like 4, 6, and 8 can all be divided by 2, so that would be, you know, more than just 1 in itself as factors, but 2 only has 1 and 2 as factors, so 2 is the only even prime number. Alright, so let's look at these examples here. So, example 1, find the factors of each number, and then classify each number as prime or composite. Okay, so basically what we want to do is we want to go through and see what numbers multiply to be 47. So we know we've always got 1 and whatever the number is, 47. And then what I would do is I would go through and check numbers to see if 47 is divisible by anything. So let me get my calculator here. And what I would do is just kind of some checking here. So I'd go, okay, I could check 2. Well, if I do 47 divided by 2, comes out to be a decimal there, so that doesn't work. 47 divided by 3, decimal again, that doesn't work. If 2 doesn't work, 4 won't work. And really, if 2 doesn't work, none of the evens will work. So maybe I could try 5. 47 divided by 5. Well, it can't divide by 5 unless it ends in a 5 or a 0, so that's not going to work. Sometimes I'll try out like bigger prime numbers like 13, so like 47 divided by 13. That doesn't come out nice either. 17 is another good one to try. And none of those seem to be working. So here there is actually no other factors besides 1 and 47. So if that's the case, no other factors there, then this would be prime. Okay, because the only factors are 1 and 47. Now we'll do the same thing with 35. So again, I know I've got 1 and 35 as factors. Then I want to see if anything else is going to go in between there. So I know it can't divide by 2 because it's an odd number here. If I try 3, so like 35 divided by 3, that doesn't work. I know 4 won't work because 2 didn't work. If I try 5, so 35 divided by 5, that comes out nice to be 7. So I'd have 5 here, 7 on that side. And then the only number that's between the 5 and the 7 would be 6. So I'd do 47 divided by 6. That doesn't come out nice. So now that I've kind of reached the middle here where nothing else works there, I know I've hit all of my numbers. So basically I've got 1, 5, 7, and 35 as my factors. So since I have just more than 2 there, this would be composite. Alright, so on page 420, try out A through D, and then I'll give you the answers for those. So, A, they got, for their factors, 1, 5, and 25, which would make that composite. B, they got 1 and 23, which would make that prime. C, they got 1 and 79, which would make that prime. And then D, they got 1, 3, 17, and 51, which would make that composite. Okay, next thing here is called prime factorization. What we can do here is we can use factor trees, which I think we've worked a little bit with this before, basically where you start with a number and then you kind of start branching off into other numbers. So like here, we're going to start with the number 36 because that's what we're trying to do the prime factorization of. And what we do is we break this into factors of 36, so things that would multiply together to be 36. So you might be thinking like 6 and 6. So if I take 36 and I break it down, 36, or 6 times 6 is 36, so I can put a 6 there and a 6 there. Then what I do is I keep factoring those little branches out, so like 6 could break into 2 and 3, same thing with this 6 here, 2 and 3. And then once I get down to a set of prime numbers, I usually circle them so I remember that they're prime. So both 2 and 3 are prime. So now I've done my full prime factorization because I got it down to just a list of all prime numbers. So then what I do is I take those numbers, so 2, 3, and 2, 3, and I multiply all those together, and all those numbers multiplied together would give me 36. Because 2 times 2 is 4, times 3 would be 12, times 3 would be 36. Okay? Now you might be wondering, okay, well, I didn't want to break 36 into 6 and 6. Maybe I wanted to break it into 4 and 9. Okay? So if I break this into 4 and 9, then I break my 4 into 2 and 2. Well, 2 and 2 is both prime. And my 9 would break that into 3 and 3. Those are both prime, and they're actually the same exact numbers that I came up with here. So no matter what you break it into, as long as they're factors of 36 or factors of whatever number, you'll still get to the same prime factorization for those sets of numbers. Alright, the next thing here, factoring monomials. So this is expressed as a product of prime numbers, so basically exactly what we just did there, and variables. And then we can't have any variables with an exponent greater than 1. So like if we had like an x squared, we would want to break that into x times x. Okay, so let's try some of these. Flip the page here. Alright, so I want to factor these. So the first thing I would do is I would take 16 and do my prime factorization. So 16 I know could break into 4 and 4, because 4 times 4 is 16. Neither of those are prime, so I keep going. I can go 2 and 2 for 4. 2 is prime. Same thing here with 4. I could go 2 and 2 there. Now I'm down to all primes there, so that would give me my prime factorization for 16. So basically I would have that that is equal to 2 times 2 times 2 times 2, because there's 4 2's there being multiplied. Then I also want to expand out my b squared and my c squared. So if I take b squared and expand it out, b squared is b times b, so 2 of those b's being multiplied, and then c squared is c times c. So times c times c. And that would be all the way factored out. So you take your number and factor it all the way out, and you take your variables and factor those all the way out as well. Next one here is 9 c to the third d. So I'm going to take 9, break that down into my factors. So 9 would be 3 and 3. Both of those 3's end up being prime. So then I would go 3 times 3, and then c to the third would be c times c times c. And then d, if there's no power there, that's just 1. So d to the first, so just a d. And then the last one here is slightly different because it has a negative. So usually what I do is I just ignore the negative till the end. And I would go like, okay, negative 15. So then I could break, okay, 15 would go into like 3 and 5. So I can go like negative 3, positive 5. Well, that would be a prime there. Now, technically here, when one of them has a negative, I can actually break this into a negative 1 and a positive 3, like that. So basically, if it's ever negative, you just have to have a negative 1 out front. Otherwise, everything else is the same. So like if I broke this down as just a regular 15, it would just break into 3 and 5. And I could just use those numbers, but then you also have to have that negative 1 out front as well. So I would go negative 1, and then my two numbers there, 3 and 5. And then there's just one of the x, so times x, and then it's y squared, so that would be 2y's multiplied out. Okay, so on page 422, try out E through G, and I'll get you the answers here. Okay, so E, they got 3 times 5 times A times B times B. F, they got 2 times 2 times 3 times 7 times y times z times z. And then the last one there for G, they got negative 1 because it had a negative. So negative 1 times 2 times 2 times 3 times 3, and then there should be 3 b's there. So times b times b times b. Okay, so that's factoring monomials. Next thing we're going to do is we're going to talk about greatest common factor. So the definition is on page 422. If you want to look at it, I'll read it to you. So it says the greatest common factor of 2 or more integers is the product of the prime factors common to those integers. So basically we are figuring out the biggest number that we can divide all of our numbers by. Okay? One way to do this is to do that same prime factorization we were doing before, and then figure out which numbers are in all 3 of those. Okay? I think that is probably the surefire way of getting the right answer. I know you might be able to look at these numbers and go, okay, the biggest thing you can pull out of all those numbers is 4, I believe. So you might be able to look at it and see that right away, but the surefire way of getting it right every time is doing one of these factor trees. So basically we're going to take each of those numbers, so 12, 20, and 24, and break them into what they're equal to. So like I could take 12, do a factor tree with that, so I could go 3 and 4, 3's prime, 4 I got to break into 2 and 2, those are prime there, so then I could go, okay, 12 is equal to 2 times 2 times 3. Then I could take 20 and break it down, so 20 I could go into 5 and 4, 5 is prime, 4 can go into 2 and 2, both of those are prime, so it would be 2 times 5. And then 24, I could break that into, let's go 4 and 6. So 4 could go into 2 and 2, 6 could go into 2 and 3, all of those are prime, so then this would be 2 times 2 times 2 times 3. Now, the next thing we have to do here is we actually have to see what's common in all of those. Those are all equals there. So what we want to do is we want to see which numbers are in all of those. So if we look here, we have at least 1 2 in all of those, because there's 2 there, 2 there, 2 there. Then I could also see, okay, well there's another 2 there, there, and there that's in all of them. Then I look and go, okay, well, there's a 3 in that one, a 3 in the last one, but there's not 3 in the middle one, so I can't include that. This one's got a 5, that's not in any of them. This one's got an extra 2, but none of the other ones have an extra 2, so those are the only things I can pull out of all of them. Then for my answer, what I do is I take those values, so like a 2 and 2 there, So 2 times 2, and solve that out. And then my greatest common factor would be 4. So 4 is the biggest number you can divide all of those different things by. So like I said, you might have been able to pick that out before you did all that prime factorization stuff, but doing that prime factorization stuff gives you the correct answer every single time if you do that. If you just guess, you might be right, but you might be wrong. Alright, next one here, we got 8 and 9. So we'll break down 8, we'll break down 9. So 8, we could go 2 and 4. 2 would be prime, 4 could go into 2 and 2. Those are both prime. So 2 times 2 times 2 for the 8. For the 9, we could go 3 and 3. Those are both prime. So 3 and 3. So here when we're looking, if we go to highlight what's the same in both, well, this one's all 2's and this one's all 3's, so it doesn't actually have anything that's common in both of those. So if you ever come up with a situation like that where there's nothing the same in either of those groups, our greatest common factor would be 1. Okay, because technically with both of those, you could take 1 times 8 and get 8, and 1 times 9 and get 9, so 1 is the factor of everything. So if you ever have a situation where you don't have any options that actually match up in both, your greatest common factor is 1. Alright, try one more like this. So this one, we've got 21ab squared and then 9a squared b. So same situation, we're going to take and expand those out. So we're going to take 21, break that down into 3 and 7. 3 and 7 are actually both prime. So 21ab squared would be 3 times 7. And then we also want to take our a and b squared and spread it out. So times a. And then b squared would be times b times b. Then we've got 9a squared b that we want to take and break down. So 9, we could go into 3 and 3. So, and those are both prime. So this would be 3 times 3. And then we also want to take the a squared and break it down. So that'd be times a, and then the b by itself. So then again, we want to look and see what's the same in both of those groups. So I know I got a 3 in the top, 3 in the bottom, a in the top, a in the bottom, b there, and then my things that are left are 7 and 3, well those don't really match, and then I got an a and a b, and they don't match together. So then when I go to write my greatest common factor here, I take all the things, so the 3 times the a times the b, and multiply those, so that would be 3ab, and that would be my greatest common factor. Okay, so you guys try on 423, try out h through j, and I'll get you some answers here. So h, they got 25, j is, oops, I skipped I is 1, so there's nothing you can pull out of those, so the greatest common factor is 1. And then J, they got 12 ABC. Okay, last thing we've got here is we've got a story problem related to factors. So what it says here is the area of a rectangle is 24 square inches, and we're supposed to find the length and the width so that the rectangle has the least perimeter. Okay, so let's talk about what area and perimeter mean. So if we got some rectangle here, area is going to be all the middle stuff. So area is equal to our length times our width. Where our perimeter, so if we got length and width, Perimeter, on the other hand, is all the way around the outside. So to find the perimeter, basically, slide this over here, basically perimeter is all the sides added together, so you would do like L plus W plus the other L plus the other W. So it's basically 2 of the lengths and 2 of the widths added together. So what we want to do is we want to find the area of a rectangle that's 24 square inches, and we want to do it so that our length and our width are the least, to make the least perimeter. So what I would start with here is I would take 24 and break it down, because I know that my area, So I got area, length times width. I know my area has got to be 24, and I'm going to try out different lengths and widths to figure out which one's going to be the smallest combination for perimeter. So if I take 24 and break it into my factors, I know I've got 1 and I've got 24. Then I go to 2. 2 will work because it's even, so it would be 2 and 12. 3 would work with 24, so 3 and 8. 4 would work there, so 4 and 6. And then the only one in between 4 and 6 would be 5, and 24 is not divisible by 5. So I would have 1, 2, 3, 4, 6, 8, 12, and 24 as my factors. Now what I want to do is I want to test those and see which one has the least perimeter. So for perimeter here, I'm adding my sides together. So I've got 2 of the lengths and 2 of the widths. So like if I try 1 and 24, that was a combination. So if I would do 1 plus 1, so 2 lengths of 1 plus 2 widths of 24, 1 and 1 is 2, plus 24 would be 26, plus 24 would be 50. So that's a perimeter there of 50. So now I want to check everything else and see if that's bigger or smaller than 50. So the next one I got there for perimeter would be the 2 and the 12. So those would multiply to be 24. I check them perimeter wise, so I go 2 plus 2, and then the 12 goes with that, so plus 12 plus 12. So 2 and 2 is 4, plus 12 is 16, plus another 12 would be 28. So that got quite a bit smaller there. So 28. Let's see if the next one's smaller than that. So the next one would be 3 and 8. So we'd go 3 plus 3 plus 8 plus 8. So that would be 6 plus 8 is 14, plus 8 is 22. So getting smaller yet. Next one is 4 and 6. And that would actually be our last one, so we'll see where this one lands. So that was 3 and 8, and now we're on 4 and 6, and that's our last group here. So 4 and 4, plus 6 and 6. So that would be 8, plus 6 is 14, plus another 6 would be 20. So that one ends up being our smallest perimeter there. So then when they ask us find the length and the width, our dimensions here would be 4 inches by 6 inches. Okay, and that would give us a perimeter of 20 inches, and that would be the smallest possible perimeter for this. Okay, so that's it for notes. You've got page 424, 22 to 54 even.